Hello guys, today we have a question from the German national competition of 2024. It asks, can a number 4, 4 and so on, 4, 1, with an uneven number of 4s be a perfect square? It's an interesting problem that I took one day to solve. I liked it and I want to share it with you guys. So the first thing that we can do is try to express this number with some sort of formula. So we have 4, 4, 4, 4, 1, so on. Well, that is nothing else than 1 plus 40 plus 100 and so on, right? And then because we have an uneven number of 4s, it needs to end in something like 4 and then an even number of zeros. Alright? Like that. And this 40 plus 400 and so on, we can actually write it as a series. So let's just write this as equals 1 plus and then a series as k goes from 1 to 2n minus 1, because we want to have an uneven number of 4s, of 4 times 10 to the k. Alright, and then whereas we have that 2n minus 1 is the number of 4s, right, for any n greater or equal than 1. Alright, so now we have a way of expressing our number that I will call z of n. So this 4441 is z of n, which equals this series plus 1. Plus 1. And we also know the formula for a geometric series. I'm going to write it on the side. Here's a side note. Side note, we know that a geometric series of the form k equals 1 to n of a times q to the k minus 1 equals a times q to the n minus 1 divided by q minus 1. Alright, for all n for all n equal or greater than 1. So we can apply this to our series in our z of n, and that would yield us that we have then 40 divided by 9. This is our a, and then inside parentheses 10 to the 2n minus 1 minus 1, and then plus 1. So let's try to simplify this. I want to get a factor out of 4/9. You will find out later why, but I'll just first expand these brackets. So 40 divided by 9 times 10 to the 2n minus 1 is just 4/9 times 10 to the 2n minus then 40 divided by 9 plus 1, which equals then adding the 1 to the minus 40 divided by 9 equals minus 31 divided by 9. And then we can factor out the 4/9 to get that z of n equals 4 divided by 9 times 10 to the 2n minus 31 divided by 4. Alright. Now I'm going to show you, now that we have this formula, right, we can now that we have this formula for our different for a set of n's, we could just go into the calculator and see which are the results of set of n. All right, and furthermore, we could take the square root to see if we get any natural number, and to check if this can be a perfect square. All right, so let's go to our calculator. Let's add our function f of x, 4 divided by 9 times 10 to the 2x minus 31 divided by 4. Alright, let's see that it's going to table indeed gives us the numbers we want. And now we can take the square root of all of this, alright, to see if we get any natural numbers. So let's see. Well, what do we see? We have these strange 6 and then point something else. So we see a pattern of the square root of set of n always being a bunch of 6's and then some decimal places. Therefore, we can conjecture that there is no such set of n that can be a perfect square, because there's always just a bunch of 6's and then some decimal places. So basically what I'm seeing here is, well, we have 6 is smaller than set of 1, which is smaller than 7. Then 6 is smaller than set of 2, 6. No, 6 right there. The square root, which is smaller than 7. Then for the third, we have 6, smaller than set of 3, which is smaller than 7, and so on. Therefore, what I'm going to try to show now is that there is always a perfect square that is so that the square root of set of n is always between two consecutive natural numbers, like I'm doing here. And therefore we could conclude that set of n can never be a perfect square. Alright? So let's form these boundaries, these lower and upper bounds. So for the lower part, we just have a bunch of 6's. And then for the upper bound, we just need the lower bound plus 1. These bunch of 6's, we can just write them with a geometric series again, like we did before. Alright, we can just write a series. I'm going to call it L of n for lower. And in fact, I'm going to call it the square root of L of n. So let the square root of L of n be these smaller numbers. So the sum from k that goes from 1 to n of 6 times 10 to the k minus 1, which then, according to our geometric series formula, is nothing else than 6 times 10 to the n minus 1 divided by 10 minus 1. And this can be simplified to 2/3 times 10 to the n minus 1. And from that follows that our upper bound, I'm gonna call it u of n. And so the square root, it equals then square root of ln plus 1, which then equals 2/3 10 to the n minus 1 plus 1. Alright, so now we have defined our lower bound, square root L of n, our upper bound, square root u of n, and we have z of n. And we know that square root of ln and square root of un are two consecutive natural numbers. Therefore, if we now can show that ln is smaller than zn and zn is always smaller than un, we show, so let's show this. So by that, we can show that Zn can never be a perfect square, as it is always in between two consecutive perfect squares. I'll say it again. We have the square root of ln and square root of un being two consecutive natural numbers. Therefore, if we square these, we have that ln and un are two consecutive perfect squares. And so if z of n is always in between them, it cannot be a perfect square. That will be a contradiction. Therefore, let's just plug the values in and let's see if this inequality is true. So ln is just 2/3 to the 2n minus 1 squared. Zn, we can copy that from before, was this value. And then our L of n is 2/3 times 10 to the n minus 1 plus 1 squared. So let's then expand the left side first. We have that, well, 2/3 to the squared are 4/9, and then 10 to the n minus 1 squared, we can just do the binomial theorem real quick to get that we have 10 to the 2n minus 2 times 10 to the n plus 1. Smaller 4/9 times 10 to n minus 31/4. And now we come to the right side. So this is a bit more complicated, but not too much either. So just let's expand this binomial theorem at first. So we have 2/3 10n minus 1 squared at first. Yet we notice that this is just our L of n. So we can just erase this and paste our former L of n. And then the rest is plus, what do we have? 2/3 times 1 times 2 times 10n minus 1. So 4/3 times 10n minus 1 plus 1. And yes, so let's simplify this. This is then by factoring out 4/9 because I wanted to divide the 4/9 from all sides. So factoring out the 4/9, we get this times 10 to the 2n plus 10n plus 1/4. Alright. Now we can just divide by 4/9 on all sides to get 10 to the 2n minus 2 times 10 to the n plus 1 is smaller than 10 to the 2n minus 31 divided by 4, which is smaller than 10 to the 2n plus 10 to the n plus 1/4. Alright, now we can just subtract minus 10 to the 2n, and then we can already see that this inequality is making sense. So let's check if this holds true. So we have minus 2 times 10 to the n plus 1 smaller than minus 31/4, which is smaller than 10 to the n plus 1/4. So first let's look at this part here. Well, we can just safely say that this is true because 10 to the n plus 1/4 will always be greater than 0, right? This will always be positive, and so it will always be bigger than the minus 31/4. So that is check. That is a check here. And now for the left side, well, for our smallest n, that is 1, we would get that minus 2 times 10 plus 1 just equals 19, minus 19, which is already smaller than minus 31/4. And for smaller n's, this value would just become smaller. Our value here would just become smaller. Therefore, this inequality holds true. This is all true, and so it is true that L of n is always smaller than Z of n, and Z of n is always smaller than U of n. And like that, we have shown, I'm just going to write it down, that Z of n is always in between two consecutive perfect squares, and it can therefore not be a perfect square. And it can therefore not be a perfect square itself, yeah.